Hi everyone. Today we'll talk about the rate limiter system design. The key aspect here is in any system design, in fact, is to ask as many questions as possible to narrow down the problem statement. So first let's go through the questions that we can ask for a rate limiter system design. Firstly, we need to know whether it's for a client side rate limiter or server side. Mostly it will be server side, but if it is client side, usually the rate limiting will happen for, say, with respect to exceptions that are caught, and if we don't want to use a lot of bandwidth sending those exceptions or error statements to a particular API server, then we have to rate limit on the number of requests that could be sent from the client side. And if the client is, say, crash looping, also we don't want to send too many requests, which will consume a lot of bandwidth. So these are some examples, but in this video we'll cover the server side rate limiter. Then we need to know what parameters are we rate limiting on: user ID, IP address, or any other parameter, preferably IP address, because a malicious user can create multiple user IDs or manipulate the other properties to impact the rate limiting, and IP address keeps it unique and consistent. And how many requests to handle, that depends on the use case. So here we'll consider probably 1 billion user IDs or IP addresses. And is it for a distributed system or a single system? Single system rate limiting is fairly easy. And should it be memory efficient? And whether the rate limiting is for which property, whether it's for comments, say, or read requests, or all requests in general, or likes or posts per day. So each of these parameters will have its own configuration. Let's say if a user is allowed to post, say, only 3 posts in a minute, or the read request should be only, say, 100 or 10 requests in, say, 10 minutes, right? Or comments or general requests can be, say, 1,000 in a day, right? So based on this, the configurations will vary, and possibly each configuration file will have these parameters independently, and rate limiting will be for each of these requests. Now moving on to the functional requirements, as we already covered, it will be server side rate limiter that we'll be covering, and preferably we'll be using IP address. It will be for a distributed system, and memory efficiencies preferable with low latency as well. And in non-functional requirements, we'll have around 1 billion IP addresses or IPs sending the requests. And let's consider if we are storing all the IP addresses in the rate limiting environment. If each IP address takes 4 bytes, then there'll be around 4 GB of data. And if there is additional, say, some metadata, right? And if we have around, let's assume 8 bytes of metadata per IP address, or we'll give, say, 24 bytes, right? So 24 bytes will be 1 billion into 24 bytes. That is another 24 GB of data. So overall we'll have like 28 GB of data, which is still quite small, which can be stored on a cache easily. Now moving on, we'll go to the system design, and the assumption here is we'll be building a middleware, a rate limiting middleware, and it won't be part of any server API server as such. Usually it can be the rate limiting can be handled in the API gateway. Or now once the requests are sent by the clients, it will be sent to the rate limiting middleware, which will get the configuration file from the rule engine cache, and the configuration file will be often read from the rule engine database, which will be updated to the cache uh, for the rate limiting middleware to be in sync with whatever is the latest configuration. And we will be using an in-memory cache like Redis, which has commands like increment and expire, which will be useful to keep a count of how many requests have been satisfied. Right, and based on the whether the condition is satisfied or not, the request will be forwarded to the API server from the rate limiting middleware. Right, so there are different ways of performing rate limiting actions. We will look at the different rate limiting algorithms that are available or that are known. So token bucket, leaky bucket, fixed window counter, sliding window log, and sliding window counter are some of the rate limiting algorithms that are known. Now token bucket, in this algorithm, there is a set of tokens that are provided, and each request uses one token for the processing, and the parameters to be considered will be the number of tokens and the refill rate, like how often should the tokens be refilled. Once all the tokens are used by the request, then the incoming request will be dropped. The con for this algorithm is updating the parameter based on burst traffic. So every time we have say a flash sale or something, we have to make sure that the token bucket parameters are updated. And even otherwise, if there is a spike in the number of requests, a sudden spike, then the token bucket parameters have to be manually or updated frequently. Leaky bucket is similar to token bucket, but in this case it uses a fixed queue size, and all the requests get into the queue, and once the queue size is reached, the incoming request will be dropped. And the con is the same as token bucket, that is updating the parameters for burst traffic. And moving on to the fixed window counter. Here there's a fixed count for the number of requests that can be sent per time window. Say for example, in a minute, count can be say 50 requests. Similarly, based on a different parameters, whether it's for comments or the general overall requests, the parameters can change. The con is we could have a burst of highly allowed incorrect or requests that are being sent when the time window is in the transition, that is say end of the first minute and beginning of the second minute. If we consider that time window, then we could have more number of requests that are sent. So as a fix to this, or as a solution to this, we could use a sliding window solution. And in sliding window, we have two ways: either use a sliding window log or sliding window counter. For sliding window log, we could use a Redis sorted set, which keeps a log of all the incoming requests along with their timestamp. And every time a new request come, the existing time period, based on the existing time period, the older logs will be removed from the sorted set, and new log is entered into the sorted set. And based on the size of the sorted set, the request can either be accepted to move ahead, or denied, and a 429 can be sent in case of a HTTP request to say that the limit has been reached. The con of this is it can use high memory because it logs every request that comes in. So if there is a high spike in the number of requests that come in. Everything gets logged in the sorted set. Sliding window counter. In sliding window counter, the value is counted based on the percentage of use in each time period. Say 70% of the previous 1 minute versus plus the 30% of the current 1 minute will be calculated, will be given a counter, and based on that counter, the request will either be allowed or denied. The con of this is that it assumes uniform distribution of requests, but it can be glitchy. That is, it can send some request that should not be allowed. But historically, it has been observed that very few requests are sent. Very few invalid requests have been sent using this method. Moving on, there are few drawbacks that we need to consider when we are handling rate limiting. Race condition is when there are two requests try to update the counter at the same time. Say one request reads it as 2 and updates it to 3, and another request is also has read the value 2 and is trying to update to 3, and up to 5 requests or up to 3 requests are allowed. Then both the requests will be allowed, and it will go through, but ideally the counter should be updated to 4 and one of the requests should not be allowed. So when we use Redis, it gets handled automatically because Redis is single threaded, and one counter will be updated only once. So it automatically takes care of that. Also, we can use Lua scripts with Redis to make sure that the updations happen in an atomic fashion, right? Or sorted sets. So in either of these cases, we can make sure that it happens in an atomic way. And consistency, we cannot have two requests reading two different rate limiter instances and counters from two different rate limiting instances. So to solve this, we'll have a centralized Redis instance or Redis server whose values will be read by all the rate limiting middleware instances. Okay, and coming to Redis, we have to decide on whether it will be a single server, multiple distributed servers with proxy, or Redis in cluster mode. Ideally, it won't be single server because if it goes down, then we don't have a backup, or we have to spin up a new server, and during the transition time, there could be some requests that will be waiting. And so we'll go with multiple distributed servers with proxy. The advantage will be that the proxy will take care of replicating to cross regions, so the requests can be read from the local instance only if we have copies of the value across the regions, right? So that helps in reducing the latency. In cluster mode, if we have a global cluster, then some of the requests will have to be read from cross-region instances. Master slave instances will also be there, so the slaves can take care of once the master goes down. But the cross-region requests will incur some latency, but it should be okay, or it depends on the use case. Okay, I think most of the points have been covered or based on whatever were the questions. So thank you everyone.